Okay, so as an example of how you might package the calculation of diagrams and correlation function in terms of matrix operations, we're going to look at systems of many pions. So this isn't directly applicable to nuclear physics because there are no nuclei composed out of purely pions. However, there is still some physical relevance to nuclear physics. When we start talking about high density matter, where you compress matter to greater than the density of nuclear matter, such as in the cores of neutron stars, then things start to populate your system in order to reduce pressure coming from Pauli exclusion. So what do I mean by that? So you can imagine that we're taking systems of lots of up and down quarks. That's what composes nuclear matter. And now we're compressing it because gravity is trying to compress the star. But as those up and down quarks get closer and closer and closer, the Pauli principle comes in, right? They don't want to be on top of each other because that's not allowed. And so this results in some net outward pressure that doesn't allow the system to collapse. And so that means that the energy that it costs to add another up or down quark to your system is very high. You have a very high Fermi energy. So at this point, it might actually be energetically favorable to start introducing new degrees of freedom. And one example is to start introducing anti-up and anti-down quarks in the form of pions, because that will relieve some of the pressure at the Fermi surface. Another example might be that you might want to start populating your system with strange quarks, and so things like kaons and hyperons might start coming into play. So the interaction between systems, between many body systems of pions and nuclei is of interest. And so just looking at systems of many pions is a first step toward that. So enough of my motivation here. When it comes to lattice QCD, we all know pions are much easier to study than nucleons. And so if we're going to develop methods that we want to use for nucleons, it might be better to look at the simpler system of pions first. So the first thing we're going to do is compose what's called a pion block. And I'm going to call that block pi, capital Pi. And this is going to be the outer product of two light quark propagators, which go from source at t equals 0 to sink at x. And notice that both propagators are at the same space-time points. So because, these are different flavors. So the thing that is left that's allowed to be different, the thing that I'm taking the tensor product of, is over the spin and color indices. And we have 4 spin and 3 color for each quark at the source and at the sink. So this means that the pion block is a 12 by 12 matrix. And we're going to use this 12 by 12 matrix to compose many pion states. So how do we do that? So you can write an n-pion correlation function in the following way. So in order to anti-symmetrize all the indices, we're going to introduce epsilon tensors, Levi-Civita tensors, the fully anti-symmetric indices. And we're going to need lots of indices here. So let me just write this first. Okay, so the pion block, the indices run from 1 to 12, which means that our Levi-Civita tensors have to be, they have to have 12 indices. So I've labeled them here, and I've separated out the first n of them to correspond to alphas, and then the remaining 12 minus n to be the Xi's. And we need another one for the sync indices. Oh, whoops. This guy, yeah, this guy runs to beta sub n, and then you have these remaining. So what I'm doing here is I'm tying up the excess 12 minus n indices that we're not going to antisymmetrize, and then leaving open the n indices that do need to be antisymmetrized. And then we also are going to need, okay, sorry, I was looking at the wrong thing. We also need n powers of our pion matrix to correspond to the n pions. And they'll have source and sink indices associated with them. Oh, not 12, n. Okay. So this is our definition for the correlation function. We have n pion matrices, and their source and sink indices have been antisymmetrized with the epsilon tensors. So, okay, how do I simplify this? How do I pull out just the diagrams that I need to calculate and determine what their degeneracies are? How many of them we are going to need? So, okay. Let's look at an arbitrary 12 by 12 matrix A and just look at some properties of that. So I'm going to look at the determinant of 1, where 1 is the 12 by 12 identity, plus lambda. Lambda is just some parameter times A. And the reason I've done this is because I can expand this piece here, and it will give me all different powers of A when I do that. So let me just do it, and hopefully it'll become clear. Okay, so first let me just write out what the determinant is, again, in terms of Levi-Civita tensors. So this is the definition of a determinant. Whoops. Okay, and then this guy runs up to 12. So this is the generalized expression for a determinant of a 12 by 12 matrix. And now I'm going to go ahead and expand this guy out. So the first term, we're just going to multiply all the ones together. So those are just Kronecker deltas that are tying up the different pairs of alphas and betas. So that just turns all the betas into alphas. Okay. The next term, we're going to multiply all ones, except we're going to use one of the lambda alpha terms. So that means we'll have Kronecker deltas contracting all but one of the betas. Okay, so there's a lambda because we're keeping one power of lambda. There's a 12 choose 1 that gives us the combinatorics for the number of ways that we can have this product. So that just is choosing which of the lambda A's we have. And then we have this guy, and then the lower one, we keep one of our beta indices, and the rest of them are all contracted. And by contracted, I mean summed over with the upper alpha indices. And then we have one power of A as well. And that ties up the remaining alpha and beta. And you can see that this pretty easily generalizes. So the nth term has lambda to the nth power. There are 12 choose n ways to get this term. And then we have n open alpha indices here. And then we have n open betas. And then the remaining 12 minus n indices are contracted with each other. And then these open alpha and beta indices are contracted through n powers of the A matrix. Okay, and then we have the last term, lambda to the 12th. 12 choose 1 is 1. And here we have all alpha and beta indices. Oops, that's a 12. Contracted with A matrices. And so this you can write in closed form. As 12 choose j for each term. We have a lambda to the j, and we have an a to the jth power. All right, now I am going to, so this was just a general property for some general 12 by 12 matrix. All right, so now I'd like to make the association that A is going to be a pion block. And you can see that if I want the, so looking at this form for C sub n, that looks like this form right here for the nth term in the sum if I exchange A for pi. And so in order to get the nth correlation function, or in other words, the correlation function corresponding to n pions, I need to pick off the term with lambda to the nth power. So I can associate C sub n is proportional to the derivative with respect to lambda to the, that's not j, that's n, to the nth power of the determinant of 1 plus lambda times pi evaluated at lambda equals 0. Okay, great. So That's fine. I've now associated a correlation function with a determinant of a matrix. But I don't want to calculate this entire matrix computationally and then take a derivative, because that hasn't saved any time. So the next thing I'm going to do is note that I can also write the determinant of a generic matrix as e to the trace log of that matrix. So this is just a general property of determinants. I can now expand the log. Okay, this is just expanding the log about lambda equals 0. And now I can expand to the exponential. And I'm just going to write out the first few terms, but you can easily write out some Mathematica code or something to give you the series expansion of this. And I'll just write out one more. Plus dot, dot, dot. Okay, so I've expanded this expression, and you can see that in order to, for example, calculate the 3-pion system, the 3-pion correlation function, I should take my pion block and calculate this quantity right here. So I can cube it and then take the trace. I can square it, trace it, and multiply it by the trace, or I can trace it first and then cube it.